All right. So, okay, let me take the highlight. Today we will discuss an overview of this paper here, Quantum Engineer's Guide to Superconducting Qubits. There's other reviews that one can consider, but I like this one, so that's why we are doing this one today. There's the archive link here, will be posted in the also together with the video. Okay, so 1904.065060. Okay, so can find it easily on the archive. Today we will do a little bit of an overview because strona in Polish down on the bottom of the screen. That means here how many pages? 67 pages to read. So these are a little bit tutorials, which means that I'm also dissecting a little bit how to even approach reading a more serious paper like this, because 60 pages, if you would be reading 1 page per minute, is more than an hour. I mean, there's 7 pages of references, so maybe 1 page per hour, you would need to finish it in 1 hour, but that's not very realistic. So our reading pace is actually a bit lower. So that's why longer papers have the organization of the article, but actually usually you can skip it if you have a nice table of contents like that. There are 4 relevant chapters, and each of them is a little bit of like a theme of a lecture course. Okay, so the second part, the key part here, is qubit Hamiltonian engineering. So wait, I will try to make it nicer. So in this part, qubit Hamiltonian is in the center. So you will be thinking more about physics of the system. Okay, once after 10 pages or so, you are happy with the physics of the system, then you continue. Okay, if you don't want to be working on the physics of the system, then you maybe skip this section, but skipping sections is actually a difficult art in reading papers. You can try to see if that works for you. So I will zoom in a little bit more. Now, how do you see kind of what's going on in this section? You kind of look at the points. And to me, I think that the most interesting gain from reading it carefully is to know how you're controlling a superconducting qubits. Okay, so B.1, so section 2, point B, point 1, will tell you about the split transmon, which is kind of the state-of-the-art technology. So after reading this, which is probably relatively heavy, so that will take you maybe 2 hours. Let's say, I will say maybe 2 hours spent on this section alone if you're reading for the first time and you never studied it before. Yeah, then maybe yeah, I see actually that the camera is not working today. Yeah. So maybe we'll be working like this better. Sorry, okay, different setup. So that way you can see me on camera. I don't need to write too much. Should be fine. Yeah, so if you're reading for the first time, this is already one session. It's a good session because if you read this for the rest of your life, you will know how this transmon technology works. So this is a lot of physics knowledge that you get. So probably like one session already. This is extremely cool because this will tell you not just what everybody is talking about, but like kind of like the physics challenges in the lab. So that's a really fascinating subject. And if you ever work on quantum control for qubits and so on, then that's pretty good. Yeah, so in short, I like this paper. What else to say? When you're reading a long paper like this, there's the really heavy lifting that might be somewhere here. And then there are maybe more research overview subjects. So this is a review which is also written at a given moment. 19 means that this was like, what, 2019 maybe? First release of the paper. The last date is here. Sorry for crossing it out. 2021. So it's been updated a few times. Yeah. So that's more or less where you kind of check at which stage it's the state of the art. Okay. So we are here. Section C is something that really is quite inspiring to me, but you can choose your own sections, which sections you like and so on. Okay. So, and you kind of see that I told you this is quantum control and how we do control and so on. You don't see it, but based on reading it, you should then become familiarized with this kind of nomenclature. So coupling axis, transverse and longitudinal, it's something that you should take from the paper. And basically what transversal means that there will be something like IT, E, ITX. So basically we will have a transmon with some levels. We will make a 2-level approximation. So this will be our 0, this will be our 1. And basically sigma x has in some way the power to be maybe switching those states or doing some adding coherence to the state of the system kind of modeled by this 2-level approximation. So so that would be probably, I think, transversal in this nomenclature, and longitudinal would mean that you're just changing the phase of the qubit here. So maybe there's some omega here and some time t, which means that you're kind of adding a phase onto the single qubit. Okay. Then you have physical couplings here, capacitive and inductive. The inductive is maybe not such a big role, but if we have a transmon here, we can bring them close to each other, and then there will be some separation between them, which will be some capacitance C. And that's more or less allowing you to exchange excitations between qubits. And that's basically something that will create ultimately evolutions of this type, only that this will not be the Ising coupling so much, but the I-swap interaction of 2 qubits is much more natural for transmons. Okay, so yeah, we are just looking at the table of contents, and we more or less know what we want out of a review that is describing superconducting qubits. We want the review to tell us what this picture means. So that would be section 2, A and B, let's say. And then section 2C.2 is this longitudinal versus transversal couplings. And the interaction, which is an important term, entangling gate. Entangling gate and stuff like this will be described. Where will we have it? I think there was quite a nice section. Here's a little bit of an overview on universal quantum computer, gate set synthesis, and so on. So around here, you will have some discussion about universality, a quick overview. If not enough for you, then you need Nielsen-Schwank. Okay, so this is more or less about universal quantum computing, but kind of in the setting of the review, which is more focused on hardware. Yeah, I think the nice thing about the review is that it's telling you all this stuff about the hardware here, about entangling gates maybe and so on, but also really about the hardware implementations. Okay, so we are kind of dissecting this already. So if we know more or less what it means to build a universal quantum computer, so good single qubits, the possibility of accessing all possible qubit states on the block sphere, and then coupling qubits together, then basically you more or less know what we will have in section number 2. Okay, so this is basically not a proposal for qubits anymore, but more or less an overview of how those proposals have been realized. Okay, so the references for the people who were kind of spearheading this effort you will find here, and so on. That's more or less what you will find in section 2. A little bit of like how this goes on the hardware side. Okay, once we are happy with this overview, yeah, then we forget everything that we were doing this, all those details. We are just like saying we know this already, and then you continue because the pacing changes a little bit here. Okay, so what happens next? There's quite a heavy section, and why is it heavy? Because the engineering is heavy. Why is it like so long? It's because it's important, because here you need to squeeze out every little tiny bit of coherence and performance of those qubits, because there's a lot of noise types that are making, you know, the job of building this quantum computer quite hard. And it's quite a good structure to say, after noise, after we have done with noise, let's think about control, and let's think about universal gate sets. Yeah, you can think about universal gate sets if you want to, you know, study quantum computers and so on, but ultimately, if you want to build a quantum computer, the pathway is through the pain of understanding noise, because dealing with noise is really necessary. And that section is not easy. It's a lot of engineering. I'm a physicist, so it's a little bit harder for me to read it. But if you take your time to read it, you really understand what goes into all this stuff. So, yeah, there's a lot of stuff to do. Yeah, so I would put a smiley face on this, and it's a good section. Yeah, it's a good roadmap and gives you a good overview on what really needs to be done, and maybe that way you can also do consulting for the hedge funds to tell them when the quantum computing promise will be delivered. Yeah, so just this kind of stuff, noise spectroscopy and so on, even how to do it, it's fairly complex. So just to give you some ideas. So types of noise, this is a little bit of like an encyclopedia, but it's written with like physics in mind, so it's not too bad. Okay, so I don't know what's going on with, okay, like this. So 12 until 17 starts quite easy. Block sphere representation, Bloch Redfield model. This is stuff that you should with pleasure do on the weekend, just for the joy of learning something elegant. And then after you do this is more or less where elegant stuff is stopping for you know, dealing with noise and stuff like this. That's more or less the end of the story, where then basically it becomes noisy in a way that is hard to treat. Okay, so let me highlight this. So Bloch, this is relatively standard textbook stuff, but then once you're happy with this, you go to 3 and 4, and that's more or less the engineering of this. Noise power spectral density means there's a process which is kind of Markovian, and it's kind of like shaking up your system. That's something you need to be able to take care of. These days, people also think a lot about non-Markovian stuff, or maybe this 1/type noise, because it's hard to get rid of. But basically this power spectral density, if you ever have to work with this, that's kind of the language that you need to do. So at minimum, like try to know the language, or like why people care about it and what does it tell them and so on. Yeah. It's not easy. I mean, it's already 1 or 2 pages. So again, like a couple of hours, right? So yeah. The noise examples are nice because it also tells you a bit of the history of superconducting qubits. So charge qubits came in the beginning, I believe, and charge is quite tough because it might tunnel onto your some charge might tunnel into the system and then basically flipping your qubit state. I would go as far as saying that maybe similar to what you would be dealing in quantum dots. So maybe worth as a physicist knowing what was going on for the charge qubits and so on. Then magnetic flux noise important because that's maybe some noise that we are dealing with, for example, in flux qubits and so on. Photon number fluctuations. I actually like this section here because I was learning new stuff. I think that might be something, maybe we will be able. So somewhere here we had the fluxonium qubits. Let me see if I can pull it up. So flux qubits and fluxonium. Those things are designed to have a good working point, and maybe is the way that magnetic flux will be kind of mitigated. I think photon number fluctuations will still stay on to give us challenges to earn our salary. Quasi-particles was quite fascinating because it's more like condensed matter theory entering into the field and solid state physics. I think it's possibly a large area where in the future maybe there will be possibilities for making the qubits better. I like the section. Okay, operator form of qubit environment interaction, so standard quantum lectures maybe, but if you read this, for example, and you haven't seen this before, that allows you to understand what's the meaning of T1 and T2, I guess, T dephasing times, how it's related to different spectral functions and so on, and how to do noise spectroscopy and try to extract this in the lab. So those are basically quantifiers of how good qubits are. Yeah. So this kind of stuff, what you will be getting out of it. I realized that I wasn't writing maybe how many hours things are taking. So I think I would write here 2 times 1.5 hours. It's not very easy. I mean, like if you're quick, you will do it in 2 hours. If you do it properly, you will need more than 4 hours, I guess. So just as an estimate. This kind of stuff here you can read fast, so maybe 13 minutes. But at some point, maybe you want to spend more time, so you maybe do 2 times 30 minutes. Okay, so another hour. Block sphere representation and stuff like this. I think this is worth actually googling some tutorials a bit for this, but let's say this is taking maybe between 30 minutes and 1 hour. So let's write 1 hour. And this stuff you see, it's starting from 13 and all the way to 18. So it's 5 pages if you read 15 minutes per page. So let's put 2 hours because I mean, you should think at times as well, right? So 2 pages here, common examples of noise. It's quite a dense section, I think, but let's be optimistic, 1 hour. Okay, this operator form comes later. I would put actually maybe even 3 hours here because you should look at the plots and actually try to digest it. I think it's like 3 hours well spent, worth spending this time. You can do it in 3 minutes, but depending what you go for. So already looking a bit formidable because what do we have? 5 hours in the second section, 3 hours here. It was like maybe 2 hours. So speaking 12 hours already, maybe in total we will get 1 week of reading. Yeah, so this is things that make us happy, that those mitigation things in fabrication are possible. Let's say 1 hour and say like, yeah, you guys will get it done. Yeah, so if you seriously want to spend time on fabrication error mitigation, then you would be reading all the papers cited there. So this is more just a teaser and an abstract for essentially a field of research in its own. So won't be the subject of our work here, but I think worth your time. Yeah, to appreciate that this is interesting stuff going on there. So how to dissect this? Okay, so depending whether you know Nielsen-Schwank inside out and some control papers, this is maybe, I don't know, it's 4 pages, so it's at least 30 minutes, maybe 30 minutes for 5 pages. Yeah, let's put 1 hour still if you read the whole thing, just to see about the notation. You could do it maybe in 15 minutes if you know the stuff inside out, but if you are reading it for the first time, there will be some backlog that you need to take care of. So I would say 2 hours, but very enjoyable. This is like, yeah, this is kind of the fun that everybody enjoys. So I will put some colors. This is like party and everybody happy. Okay, so that's the kind of cool stuff why we want to do quantum computing. This is more like an abstract section. So it's conveniently abstract, so not so much pain of dealing with the hard stuff like noise, but you deserve it if you read the noise section before, right? And then you kind of get a sense for the gap that you are dealing with. Okay. So for sure, if you read those sections, it's good to understand what serious experimentalists and a serious review and so on, what they are looking for from Nielsen-Schwank. Yeah, so it can be a reference section for you to inform your reading of Nielsen-Schwank's textbook. Okay, so single qubit gates. So that needs this kind of sections number C, yeah. But this is already quite fun. This is quite good. So single qubit gates here, capacitive coupling for XY control. So you might add like an oscillator capacitively coupled to your qubit. Virtual Z gates. It's first time I saw this here. That's also something that happens in reviews. That's the point for reviews, so that even if you're more or less in the field, you update your state of the knowledge and yeah, and basically before textbooks come around where everything is more or less becoming classical contents and so on, it's like reviews bring in this kind of stuff that will probably stay on. Probably any successful large-scale quantum computer that that will use superconducting qubits will make use of virtual Z gates. The drag scheme we will maybe cover in detail using other papers in this kind of series of tutorials. That's basically, let's say, doing some operations to stabilize the system. Yeah, so this is also showing you where theoretical ideas, those 2 sections, show you where theoretical ideas that are strongly rooted in the hardware can really inform experimental efforts how to do stuff. So in that sense, that's maybe also a nice perspective. If you want to be in the field of superconducting qubits, definitely something that you should try to understand carefully. So we have 3 pages, but I will put 2 hours here because there's a lot of formulas there. And I think this is 2 hours for all the formulas. I think this is optimistic. iSwap gate, isn't it nice? Okay, it's nice. iSwap gate I don't know if that's wrong to say. It's not wrong to say. It's a 2-qubit gate that, let's say, it's the equivalent, that's the experimental equivalent of a CNOT. Okay, so in theory, everybody works with Cliffords, and in Cliffords we talk about the CZ gate or CX gates. In this kind of superconducting business, ISWAP is much more natural, just popping up, and this section just tells you about how to go ahead with that gate for universal quantum computing. So in the previous tutorials, just as a reminder, we were talking about universality and compiling, and we basically stated, without even maybe giving the reference, that a universal gate set is entangling gates, a single type of an entangling gates, which can be the ISWAP, and single qubit control, right? So single qubit control part is here, 2-qubit entangling gate is here. So jointly we have universal quantum computing scheme. Yeah, it's not realized yet, but like they are saying this is fairly realistic, and they are basically giving their progress report on how they are going towards that really in the lab. Okay, so let me clean up a little bit. Okay. So this is universal, not university, universal quantum computation. That's probably then the scheme. Okay, going all the way here, and this was 1 hour. So C phase, I would say maybe on first reading you can view this as a variant maybe of like some ISWAP. And basically to give you an example of how knowing the physics of the system and being close to experimental applications allows you to come up with other 2-qubit gates. Okay. Just one thing that just popped to my mind. If you're reading section number 2, you should understand the difference between phase tunable couplings, qubits, and other types of transmons. That will be quite nicely explained, and it will be also stressed, but not something you should miss from before. And if you skip section 2 for whatever reason, then you should know that you will find this kind of stuff there, because it really makes a difference whether you have tunable couplings or for example, those cross-resonant gates. Okay, so there's a split between different approaches, the different philosophies, maybe how to set up good large-scale platforms. Okay, that was state number 1 in the scribble here. So this is maybe tunable, I write, and this is CR. Okay. And for example, when you're reading this, like the least to not be lost is to try to make a distinction and see what are the differences here. Okay, good. I think okay. Let me check because I don't see the chat directly. Okay, nothing in the chat. Guys, I post the recording if anybody wants to say something, or so far so good. We are not doing much of the paper, but it's a big paper, so that's fine. Okay, you can just interrupt on the way. Okay. Okay. So, yeah, some other stuff about those swap gates. I think the most fascinating part is when you kind of use adiabatic transitions there and try to speed it up using really the physics of the system, and that's kind of like inspiring, that really, you know, let's say really brilliant physics insights can improve the qubits. And then finally the readout, and the readout is not so trivial, as I'm learning these days. And yeah, dispersive readout stuff, I would say 2 hours to more or less on average. If you know a lot about James Cummings model and like some sort of frequency shifting and so on, then maybe faster. If you were learning this, maybe a bit longer than 2 hours. So let's say around 2 hours. And measuring the resonator amplitude. This stuff is actually pretty fun, but you need to take time for this a bit. And it's really cool stuff as well. So it's also worth 3 hours. Come on, if you're already reading that, like another day of reading. Kind of cool stuff. Then the rest you can maybe speed up a little bit unless you're the expert. So how about we say the remaining 10 pages, let's put 2, because you want to get to the summary and the outlook, which is maybe tops 1 hour to just browse through it. Okay. So on this page, we have what? 8 hours. I think it's clear that I will not do all the stuff in those tutorials. Here I was saying 2 hours. I would say 2 hours here as well. The C phase is maybe more for the expert stuff, so maybe more or less skip on first reading. And CR stuff is still worth reading to be able to compare between tunable and not tunable. So 6 hours here, 2 hours for the intro, 8, 11 hours here. And here 1, 3, 4, what, 5? 5 plus 3 plus, this is 10 hours. So in total, we have around 30 hours of reading. If you're able to, and that's kind of, if you want to use this paper to really become, you know, knowledgeable, deeply knowledgeable, because it allows you to really develop some understanding of the setup. So if you're reading 2 hours per day, it's 15 days. If you're working 7 hours, 7 days a week, then it's around 2 weeks. If you're working 5 days, then it might be 3 weeks of reading. Yeah. And that's what you're looking at. After 3 weeks of daily reading for 2 hours, you can know a lot about superconducting qubits. Okay, that's my overview. Sorry for the scribbles. It's looking a bit messy here. It's a good review. Maybe it should be, yeah, I cannot easily erase everything, but you can take your own version. So I think maybe this overview, if I summarize this, so if I summarize this, my estimate is for an advanced undergraduate student, you would maybe spend 1 month of daily reading to familiarize yourself with the stuff, maybe maybe lecture notes, for example, by Gerwin, to supplement the kind of physics stuff if you want to learn a little bit more. And maybe you will need a little bit like of Qtip and so on to learn about this kind of stuff. So maybe 1 month of daily reading. Yeah. So a bit of a serious look at this. So the idea is that the tutorials might be a bit of an overview for me to kind of dissect and remove a little bit of the work strain for I don't know why it's looking like this. Remove a little bit of the strain of orienting yourself, and then you can really spend your focused work on just you know, on the physics side of it. So an introduction, usually, let's say you should read, but we will not read it today. It tells you about the organization of the paper and a little bit of references, but a review is a little bit of an overview as well, so maybe not so much needed for us to read this here. Okay, I will stop the video now.